Hello, BC Calculus students. This is the first lesson of the first unit of BC Calculus. And hopefully this is review from either Pre-Calculus Honors or AB Calculus. But today we are going to go over everything that has to do with limits. We'll take a look at limits from a table, limits graphically, and limits algebraically. And just so you know, in calculus, we call limits algebraically, we call it analytically. So if you hear the word analytically, it means algebraic. So the first thing we'll do is take a look at the function g of x equals x squared minus 9 divided by x minus 3. This is a rational function, and we want you to complete the table of values. I went ahead and did this by using Desmos to figure out all of these values because I didn't want to sit here doing it with you online. So what I'd like to do right now is just show you the values that I found when I used Desmos. I got x equals 2.9 gave me 5.9, 2.99 gave me 5.99, and you can go ahead and copy this table of values onto your notes. And you'll see that when they ask us what g of 3 is, well, g of 3 is undefined per the table of values. So we would just write UND right here for undefined. The domain of g, because the function is undefined at 3, the domain of g is going to be all real numbers except for where x equals 3. The next question is, as the values of x get closer and closer to 3, what value does g of x get closer and closer to? So when you look at these values of x as we go closer to 3 from values less than 3 and closer to 3 from values greater than 3, my y values are getting closer to the number 6 from both directions. So that means the y values, or g of x, are getting closer to 6. We state that as x approaches 3, g of x approaches 6, and this little arrow here means the word approaches. So we state in formal notation that the limit as x approaches 3 of the function g of x is equal to 6. So in general, this notation is read as the limit as x approaches a of the function f of x is equal to L, which is the limit. So let's do a practice problem. Go ahead and take a look at this limit. It says the limit as x approaches 0 of the sine of x divided by x. And we're working on limits numerically. So what I'd like you to do is come up with a table of values on your own paper, and then in your calculator, evaluate those table of values for to find out what the actual expression sine of x over x is approaching. I will pause the video here, or I would like you to pause the video here, do this work, and then come back and check your answers. Okay, so I went ahead in Desmos and came up with these x values, so negative 0.1, negative 0.01, negative 0.001, negative 0.30 and a 1, and then I flipped to the positive side. And what I see here is that my y values, as I'm moving toward the value of x equals 0, my y values are approaching 1 from both sides. So as I approach 0 from below 0, my y values are actually so close to 1 that it looks like they round to 1. And then same from the more positive y values. As we approach x equals 0 from the positive side, we are also approaching 1. So that means the limit as x approaches 0 of the sine of x over x is equal to 1. And actually, I would argue that for this problem, we would write approximately equal to, because unless we had our algebra, we wouldn't be for sure certain that this limit is equal to 1. So we could go back up actually to this limit of g of x as x approaches 3 and also say that it approximately equals 6. And the only time we're going to get a true equal sign out is if we use algebra to simplify. So now it's time to take a look at limits from a graph. So when we work through limits from a graph, what we're trying to do is find the y value of the graph as the x value approaches whatever is notated down here. So as the x value approaches 0, what's happening on the graph is that the y values in this case are from both sides approaching the number 2. So we would say the limit is approximately 2. Moving on to the next one, we have this plus sign up here in little exponents. So x is approaching 1, and there's a plus sign. That means from the right or from above. And what they're referring to is on a number line, values to the right of 1. So I come over to the graph, and I'm coming in on the x-axis toward the number 1, and the graph is coming in here, and it looks like the y value being approached is 0. And notice that I'm writing these squigglies for approximation because we won't get exact values until we use algebra. The negative sign up in the exponent means from the left or from below. So as x is approaching 1 from below, my graph is actually up here, up here, and the y value right here is approaching 2. So I'd say approximately 2. So the next question is the limit as f of x as x approaches 1. Well, back over to the graph, when we came to 1 from above or from the right, we came in towards 0. When we came into 1 from the left or from below, we came towards 2. Those values here are not equal, and therefore we would say that this limit does not exist. And then the last question dealing with 1 is, what is f of 1? Well, f of 1 is up here, so f of 1 is approximately 2. So based on what I just taught you, I'd like you to hit pause and work through the rest of these questions, and then you can check your responses in a moment. All right, let's take a look at these problems. First of all, as x approaches 2 from the left or from below, the y value being approached is right here, it's 1. F of 2 is approximately equal to -1, that's right here. The limit as x approaches 2 of f of x, coming in from both sides here, is approximately 1, this y value right here where the hole is. The limit as we approach -3 from the right, we're coming in from the right, so we're approaching -1. As we approach -3 from the left, right here, we're also approaching -1. So since we're approaching the same value from the left and the right, that means our overall limit is going to be -1. So that what I just said was that if the left-hand limit, meaning as we approach from the left, is equal to the right-hand limit, meaning coming in from the right or above, if those two limits are equal to each other, that means that the overall limit is existent and is exactly equal to the left and the right-hand limit. In this case, f of 3 is up here, it's approximately 1. As we approach -4 from above, that's down here, we're going down to -2, and just FYI, they will not ask us about -4 from below since it is not in the domain of the graph, so that's not going to be a question you'll ever have to consider. As we approach -1 from below, that's up here, we're going to go to 1, coming in from below here, and then f of -1 is up here at approximately 2. So that brings me to the limit laws. And I don't want to spend a lot of time on these. I just want to point out in layman's terms what they mean. This says if you have the function f and the function g and the limits at a exist on both of them, that means that the left-hand limit and the right-hand limit must exist and be equal to each other for both the graphs f and g. If you add the graphs together or subtract them, you could add or subtract their limits. If you multiply a constant by the function, you can factor that constant out in front of the limit. If you multiply the two functions, you can multiply their limits. If you divide the functions, you can divide their limits as long as the denominator is not equal to 0. If you raise a function to the exponent n, you can also raise the limit to the exponent n. If you root to the root n, root the function, you could also root the limit, assuming that that root exists. And then these are two special limit laws that we use a lot. The limit of some constant function y equals c. So here is my graph of y equals c. The limit as x approaches a for any value on that graph is going to be that constant value c. And then this last one is actually the graph of y equals x right here. So anytime x approaches a for any value a, the y value also equals a, so that limit equals a. I'd like you to pause the video for a moment and try problems 1 through 4 using the graphs of f and g. For number 1, I'm just evaluating the limit as x approaches -2 of f of x, which is right here at 1. plus 5 times the limit of g of x, which is -1. So then I'm just adding 1 plus 5 times -1 to get -4. With number 2, this property only works if each limit by itself exists. And what you'll see is when you look at g, as x goes to 1, we have one limit coming in from above and a different limit coming in from below. So that limit does not exist, and therefore the overall limit does not exist. For number 3, we can divide our limits only if the denominator is not equal to 0. And in this case, as x approaches 2 of the g function, that limit is 2, so we're dividing by a 0, so this limit dne. And in number 3, I'm taking the limit of g as x approaches 3, and that is 1, and then I'm squaring 1 and getting 1. Okay, the next section is solving limits analytically. The easiest way to do this, and remember when I said analytically, I meant algebraically, and these are the old school methods because we love them and they're super easy and you learned them last year. So now what I want to do is just show you quickly how to do direct substitution. This is sort of the easiest of them. And this is when you can just substitute in 5 for your x, and your limit here is -2. Here you'll sub in 5 for your x, you'll get 25 minus 15 plus 2 equals 12. And here, this is a constant function. Remember the constant function where you have this straight line, this is y equals pi. So anywhere on that whole function, including where x equals 5, this limit is going to be pi. Next, we have cancellation. This is really used a lot with rational functions. So what you want to do is factor the numerator. So I have x minus 3 times x plus 2, all divided by x minus 3. I cancel out the whole because, of course, a whole, like this example up here, a whole does not cause a limit to not exist. So we're still good with the whole. And now that I have just the x plus 2, I plug the 3 into the x plus 2, and I find the limit through direct substitution is now 5. So let's do factoring here, x plus 2 divided by x plus 2 times x minus 2, and then cancel the x plus 2's. Let's plug in a -2, and we're left with 1 over -2 minus 2, which is -4. Now this last one is a rational function, but don't get excited because you can't factor and cancel anything. So this one you're going to have to call on your knowledge of graphing rational functions. We spend a lot of time calling on our prior knowledge in this course. So this is going to be a hyperbola that is shifted right by 3. So it's this general shape here, and then another branch over here. So our core 1 over x function shifted right by 3. We have a vertical asymptote here at 3, goes up to infinity coming from the right, down to -infinity coming from the left. So that limit does not exist, dne. So now we have some methods that are trickier and take a little bit more time and effort. So I'm going to go ahead and do this rationalization. It says rarely used, and quite honestly, not used much in AB Calc, but in BC Calc we will see it, so we do need to learn it. You're used to rationalizing a denominator. Like if you had 1 over the square root of 2, you would multiply by the square root of 2 over the square root of 2. In this case, our radical is in the numerator. So what we're going to do, oops, I meant to put a multiplication sign in there, hang on. What we're going to do is multiply by the conjugate of the expression in the numerator because this one includes the radical. So we have 1 plus 1 over x divided by itself. And I want to FOIL my numerator. So I have 1 times 1 is 1. My middle term, which is the negative radical times 1, and then 1 times the positive radical, those will cancel out. And then my last term will be a negative times a positive, so a negative. And then I have the square root of 1 plus x squared. And in my denominator, I am not going to FOIL it out or distribute. So when you do these rationalization techniques, what you want to make sure to do is FOIL out where you multiplied by the conjugate. And remember, the conjugate is just the opposite sign between the two terms in the expression. So I had a negative here, multiply by the positive here. So FOIL out where you multiply by the conjugate and leave the other one unsimplified. Now, I'm going to clean this up in the numerator by squaring the square root of 1 plus x. So I'm going to have 1 minus, and in parentheses, 1 plus x all over the x times, in parentheses, 1 plus the square root of 1 plus x. And now in my numerator, do you see how 1 minus 1 will go to 0, and I'm left with just a negative times the x. So my numerator simplifies to negative x. The reason why I did not go ahead and simplify my denominator is because now my negative x and my x will cancel, and I'm left with a negative 1 over 1 plus the square root of 1 plus x. And I can finally use direct substitution and sub in the 0 to get negative 1 over 1 plus the square root of 1 plus 0, which is 1. And my answer is negative 1/2. So now what I'd like you to do is take a few minutes, hit pause, and go ahead and do your best to answer these questions, either using direct substitution, by using factoring and canceling, or by using something a little bit more creative, which is what you're going to have to do here for number 5. This might take you a few minutes to do, and that's okay. Hit pause and come back for your answers. Okay, great. Let's check your work. On the first one, I used direct substitution, and when I plugged in x equals 2, I got out 15. The second one, I also used direct substitution, and when I plugged in x equals 0, I got out 0. The third one I'm hoping you recognized from the very first page of this lesson. I factored my numerator, I canceled the factors, x minus 3, and then I used direct substitution. Notice this time I'm allowed to say that the limit is equal to 6. No longer is it approximately equal to 6, because when I use algebra, I get a definitive answer. Number 4, I'm betting most of you tried to use difference of squares in the numerator and denominator, and then you might have gotten stuck. But there's a nice trick on this one where if you just factor out a negative from your denominator, you'll end up with the factors of x squared minus 1 over x squared minus 1 that canceled, and you'll be left with 1 over negative 1, which is just negative 1, and my smiley face is for the nice trick. This next one you might recognize as being representative of the definition of the derivative at a point. You might have known that from pre-calc honors or AB calculus. So I actually tackle this one by foiling this expression to get 9 plus 6 times delta x plus delta x squared, and then minus 3 squared is minus 9. My 9's cancel, and then nicely I've got a delta x in each of my remaining 3 terms, and that leaves me with just a 6 plus delta x, and then I can take the limit as delta x goes to 0, and I get my answer of 6. The last type of limit that we'll be talking about today are limits at infinity. And these we deal with many times with just rational functions where you have f divided by g and where f and g are both polynomials. And this goes back to what you learned in Algebra 2 honors, pre-calc honors. Basically what you want to do is look at the ratio of, you want to look at the highest degree exponent in f versus the highest degree exponent in g. And we're going to go with the fact that of the function 1 over x, and I drew this on another page, but the basic graph of 1 over x, as x goes to infinity, do you see how there's an asymptote here, and the y value goes to 0? That works the same for x going to negative infinity. So we use that as our basis. We take a look at the first one here, and we have a larger degree in the denominator, because in the numerator, our degree is 1, and in the denominator it's 2. So your limit at infinity is going to be equal to 0. This isn't equals because these are hard and fast rules. The next one has a degree of 4 in the numerator, a degree of 3 in the denominator. Because there is a higher degree in the numerator, our limit will either be quote unquote equal to positive or negative infinity. In this case, because we have 4 over 37, and we're going to where x equals infinity, that means our end behavior will look like this with a slant asymptote. So that means that this limit is technically infinity. But this is where we can have a nice discussion about whether infinity is even a limit, because infinity is really a concept, and infinity by definition has no limit. It is a limitless value. So what Mr. Walker and I like to say for these types of questions is the limit does not exist, because it is our belief that infinity is not a limit. The good news is the AP College Board will never give you a choice between these two answers. They will never ask you, is the limit infinity or is the limit does not exist? They will give you one or the other, and it is totally okay to use either one. We caution you though, because what if, let me change colors to show you a big what if. What if this 4 out in front here had actually been a negative 4. Then I would have had a negative 4 over 37. My end behavior would have looked like this, and the actual limit would have been negative infinity. And if you had said infinity and the actual limit was negative infinity, you would have gotten it wrong. However, if you had said does not exist, you would have gotten the correct answer, whether the answer is technically infinity or negative infinity. So what Mr. Walker and I like to impress upon you is that you want to just give does not exist anytime you have a larger degree in the numerator versus the degree in the denominator. The last type of problem is when you have the same degree in the numerator and denominator. So 3 and 3, then you just look at the ratio of the leading coefficients. So the leading coefficient here is a 1. The leading coefficient here is negative 2. So this limit at infinity is negative 1/2. So basically, if the degree of f is less than the degree of g, then the limit is equal to 0. So that's a smaller degree in the numerator, larger degree in the denominator. If the degrees are the same in the numerator and the denominator, the limit is the ratio of leading coefficients. And then if the degree is larger in the numerator, then the limit does not exist. And then we have just one last topic here on this page, which is called the squeeze theorem. And the squeeze theorem basically states that if you have a function g and you're trying to find the limit of the function g and you don't know how to do it, you can't use algebra, you're kind of stuck. Well, if g is between a function greater than or equal to f, less than or equal to h, and you know what the limit of f and h are near some value a, okay? Doesn't matter what happens at a because g of a could be undefined, like there could be a hole there, an asymptote, don't worry about that, just needs to be near a. Basically, if these two limits, the limit of f and the limit of h, are the same and they equal L as our limit, so the limit below g is L and the limit above g is L, that means we've squeezed our limit to be L. And let me show you how this works. So we don't know what the limit of x squared cosine of 1 over x squared is. But I do know that cosine of 1 over x squared has to be less than or equal to 1 and greater than or equal to negative 1 because I know that the range of a cosine function is from negative 1 to 1. And then I can multiply all three parts of this inequality by x squared. And the x squared, by the way, is coming from this component right here. So that means I have negative 1 times x squared, or negative x squared, less than or equal to x squared cosine of 1 over x squared, less than or equal to x squared. And we were trying to find the limit as x approaches 0 here. So if I do direct substitution and plugged in 0, I get out that the limit on the left is 0. And if I do direct substitution here and plug in 0, I get the limit on the right is 0, which means that this overall limit is squeezed between 0 and 0, and therefore the limit is equal to 0. Next question, we could do the exact same way, except for the fact that I don't have a guaranteed range of my e to the sine of 1 over x, so that is a problem. So what I'm going to do is the following. I'm going to use the fact that I know that sine of 1 over x does have a restricted range. So sine of 1 over x has to be less than or equal to 1, greater than or equal to negative 1. And then, since I really needed e to the sine of 1 over x, I'm going to exponentiate with a base of e on all three sides of the equation. So e to the negative 1 is actually 1 over e, and then I have e to the sine of 1 over x in the middle, and I have just e on the right. Well, now I'm going to have to multiply by that x squared. So I have x squared over e is less than or equal to x squared e to the sine of 1 over x, which is what we're trying to find the limit of, is less than or equal to e times x squared. Now, if I go ahead and plug in by direct substitution 0 into x squared over e, I know that my limit is 0. Same thing on the right, if I plug in by direct substitution x equals 0, I know that this limit is 0. So my overall limit is once again going to be 0 because we're squeezed between the limit of the lesser function of 0 and the limit of the upper function as 0. That wraps the core lesson. What you have left to do now is a set of practice problems in another presentation.